Hello everybody, welcome to the new installment of our component-based software development course. Today we will see the strategy pattern, which is arguably one of the most popular design patterns in industry today. But to start with the strategy pattern, we need to understand what a design pattern is. So a design pattern is nothing more than a solution to common problems in software applications around the world. 30 years ago, I would say even more, like 40 years ago, we had a bunch of software engineers that decided to compile a book showing common problems in software applications around the world. They thought to themselves, if we propose a solution for this type of problem that we are having here in our company, in our academic environment, or wherever they were, some people from another country can benefit from that solution. So several of these software engineers decided to propose solutions to these common problems in software design, and they called it design patterns. In the study of design patterns, we do not focus on any programming part of it. All we care is how we structure, how we build, how is the architecture of our software application. That's all we care about. It's all about the good practices in the object-oriented paradigm. One interesting citation quote from the book is, we can see it as a description or simply a template for how to solve a problem that can be used in many different situations. So to start with our strategy pattern, let's start with a simple example of a simulation duck app. So this is basically a game, and it shows a variety of duck species swimming and making quacking sounds. And it uses standard object-oriented techniques and one duck superclass from which all other duck type inherit. This is really important for us to remember and to have a good review of object-oriented paradigm. So here we have our superclass duck, which has quack, swim, and display, and any other duck-like methods you want to create. So we know that all ducks that are instantiated from this class, from this superclass, will inherit the quack, swim, and display. So a mallard duck, for example, I will overwrite the display method for it. So I will print something like, looks like a mallard, okay? And if I have another duck, for example, the red-head duck, I will also override that display and print a different message. And other types of ducks also inherit from this duck superclass, okay? So each duck subtype implements its own display behavior for how it's going to look on the screen. And the display method is abstract, since all duck subtypes look different. But now we need the ducks to fly. So we need to create a new ability to fly. So this game evolved. It's an upgrade of this game. It's a new version that ducks will fly. So how to implement that? What seems to be a good approach? Well, we can just add the fly method in the duck superclass, and then everybody else will just inherit it. So we add the fly. So we have the mallard duck now with the fly behavior. We have the red-head duck and any other ducks that can inherit from that. But something went horribly wrong. There were some rubber duckies in the game. They started flying around the screen, because all subclasses of duck should fly, since the fly method is in the superclass. So everybody inherited that, even the rubber ducky. So they thought that this was a great use of inheritance, but they forgot that maintaining the code, the maintenance, can be costly. So this is what happened. By putting the fly in the superclass, all ducks now fly, including those that shouldn't fly, which is the rubber duck. So think for a second, what should be a good approach to that? And also, we know that rubber ducks, they don't quack, they just squeak. So we also need to override that quack sound. So override the fly method in the rubber duck can be a solution, just like we did with the quack. So if override the fly method in the rubber duck, we can solve this issue. But what happens when you have like a wood duck they can't quack or even squeak, and they cannot fly. So do you see the problem? Do you see that as we put more types of duck, some of them will have to keep overriding? So the rubber duck will override the quack to a squeak, and the display is also a method that will override the fly, and then the decoy one, the wood one, we also need to override. So here's another class in the hierarchy. Notice that the decoy does not fly and does not quack. So how about an interface? Maybe inheritance was not the answer for us here. So if the company wants to update the product every 6 months, the employees would have to, the programmers would have to trace back to all these types of ducks and make sure they're all doing the right behavior. So they'll have to look at and possibly override every fly, quack methods for every new duck subclass ever added to this program forever, and this can cause a nightmare. So how about an interface? So for example, we just say that ducks swim and display, and we will have a interface called flyable and one called quackable. And just the ducks that fly, that have the flyable behavior, will inherit from them. So mallard duck will implement flyable because it needs to fly. Mallard duck will implement duck because it's a type of duck. So we have another interface, quackable. Whatever duck needs to quack will implement it. So we know that mallard duck will implement flyable behavior, quackable behavior. Red hat duck will implement the flyable behavior and the quackable behavior. The rubber duck will implement only the quack behavior, and the rubber duck will not implement flyable or quackable because, you know. And so what we did was we removed the fly method from the superclass and also the quack one and create interfaces for them. So only the ducks that need to have that will implement the interface that needs to have those methods. But the problem here is reuse. It solves part of the problem. We no longer have flying rubber ducks, but whenever you need to modify a behavior, you need to track down and change it in different subclasses. Whenever you need to change the quack, you need to make sure that everybody that implements quack will suffer those consequences. And are these consequences good or not for my purpose, for the purpose of the game? So we have another maintenance nightmare here. So different flying behaviors, for example, can cause issues for us. So the first design principle here is to identify the aspects of our application that vary and separate them from what stays the same. This is a strategy pattern. It seems really simple, and it is. So take what varies and encapsulate it so it won't affect the rest of your code. So as a consequence, we will have fewer unintended consequences from code changes and more flexibility in the system. So let's separate the parts that change from those that stay the same. So we'll create two sets of classes apart from the duck. We know that fly and quack vary across ducks. So one just for fly and one just for quack. And we'll hold the implementations of their respective behavior. We will not have them in an interface itself. So if, for example, one class implements quacking, another that implements squeaking, and another that implements silence, these should be separate. So here is how it looks like. So we have the duck superclass, and we have several duck behaviors, for example, flying behavior and a quacking behavior. But you can see that inside flying behavior, we see that it has its own set of classes, and each one of them will take care of a different flying behavior. So a duck, a new type of duck, does not have a flying behavior, an abstract flying behavior. It actually has a flying behavior specific for its purpose. So we keep things really flexible in this way, and we will assign behaviors to each instance of a duck. So for example, if we have a new mallard duck, we'll initialize it with a certain type of flying behavior, and we should be able to change those flying behaviors at runtime. So following the first design principle is still in the strategy. We know that we need to program to an interface, not to the implementation. So we use an interface to represent each behavior, and each implementation of a behavior will implement one of those interfaces. So the duck class will no longer implement flying or quacking interface. It doesn't even see those. It's completely separate. So the solution is to make a set of classes to represent a behavior, for example squeaking, and this behavior class will implement the interface. This way we will have duck subclasses that uses behavior represented by an interface, so that the actual implementation of that behavior will not be locked into the duck subclass. So let's see how it's gonna look like. So we have now a fly behavior with a flying method, an abstract one, and we'll have other classes, for example, fly with wings, flying away, that implements the type of flying with wings, and for flying away we'll implement a fly behavior that is a non-existent flight. The elements that cannot fly. So we will have an overview of this fly behavior, like fly with wings, flying away. When we do the same for the quack behavior, so quack implements that interface, squeak implements that interface, quack no way implements that interface. So what we have here is different types of quacking separate from the interface. They all implement quack behavior because you have that method, that abstract method quack. But each one of this will hold the what is special about each type of quack. So this is an interface that all flying classes implement. So if you have a new type of flying, all it needs to do is implement the fly behavior. If you have a new type of quack, all you need to do is implement the quack behavior. So this way, other types of objects can reuse our fly and quack behaviors because these behaviors are no longer hidden away in our duck classes. And it's possible to add new behaviors without modifying any of our existing behavior classes or even touching any of the duck classes that use fly and behavior. So, in summary, let's have a big picture here of these behaviors. So we have the duck superclass, which has two instance variables, the fly behavior and the quack behavior, meaning that each duck that implements the superclass duck, each subclass duck that implements duck will have a certain behavior, or a fly behavior or a quack behavior, regardless of what they do, but they all need to have a fly behavior and a quack behavior. And the methods that all subclasses will inherit are swim, display, a perform quack, whatever the behavior is for that, and a perform fly, whatever the behavior for flying is. And we need to be able to change the type of behavior on the go. So what does that mean? So when you instantiate an object of a certain type of duck, for example, let's say the rubber duck, when at the time of birth of that object, I like to say that, when that object is created, it is born with a certain fly behavior and quack behavior. But what if it changes? What if you somehow want the rubber ducks to start flying out of nowhere? You can, maybe. There's a new release of this game and you want the rubber ducks to start flying as a new trend or something. So you need to create functions, methods, setters, set fly behavior, set quack behavior, that change the behavior after the object is created. That's the purpose of these functions. We'll see in the code. So several ducks will implement that superclass duck. So for example, the Malar, the rubber, the red hat, and the decoy one. And they all have their own display methods. So display is something that we still have overridden for each one of them. And the behaviors so far are the fly behavior and the quack behavior. So examples of fly behavior is fly with wings and flying away. Examples of quack behavior is quack, squeak, and quack no way. And think of these as algorithms. Like think of this as actually what is this quacking, squeaking. So you see that the duck don't see those behaviors anymore. The only thing is a variable called fly behavior that is used to represent this fly behavior interface, and the quack behavior instance variable to represent the interface quack behavior. So I think everything will become even more clear as we code this example.